All right. So rather than being like Dylan and just coming up and down and up and down, they're just having me stay here for 20 minutes. So we're going to talk about structural engineering and fire for about 20 minutes. So if that's not interesting to you, it's a really good time to check your email. Um, so we're going to start talking about steel mass timber hybrid floors. And this project is co-funded with the Charles Pankow Foundation and the American Institute of Steel Construction. So this project is funded by both the timber industry and the steel industry, which I think is it's pretty cool. And this is really motivated by a lot of the buildings that we're seeing pop up around the United States. These steel mass timber buildings are being constructed not just here on the West Coast, but there are a number of buildings being constructed in the southern United States as well as eastern United States. And there isn't a real clear way of an understanding of how the mass timber floors and the steel beams act compositely with one another, or when you might want them to act compositely. Do we want it for strength or stiffness, or how does the diaphragm actually work? And so this project really aims to dive into that, and we're kind of in the middle of it. I do want to acknowledge that I'm not the only person on this project. This is in collaboration with Mark Fretz at University of Oregon, as well as Adam Phillips at Virginia Tech. And so I'm going to focus mainly on the structural testing today, and then kind of give you the bigger picture of how we're working with Mark and what our end goals are there. And so we did a number of small scale direct shear tests. So we varied the number of kind of in the type of connectors that we're looking at, from screws to bolts. And we really wanted to categorize the connectors themselves. There's been a lot of work on this in Europe. There's been a lot of different connectors that have been tested. And so we aimed to then combine our data with what is already out there to get a better understanding of kind of the lay of the land of how these connectors are behaving. And then we performed a number of beam scale tests. So we were looking at vibration. How does the natural frequency of these beams change when you're changing the connector type? Do we get composite action at these low amplitude loads? We looked at flexural stiffness, so loading them under service level demands. Do we get composite action at service level demands? And how does that change if we look at beam scale or if we look at girder scale? So girder specimens where the CLT major axis is parallel with the beam span, and the beam specimens where the CLT major axis is perpendicular to the beam span. And then lastly, we took a few of these specimens and we loaded them to failure. So looking at that full range of loading on these specimens and what is controlling failure, how do the connectors behave, and then also kind of linking in these small scale tests. So we have kind of the full range of behavior of these connectors. And so how do we then link it into the beam scale? And so where all this is going is you've heard about a lot of different floor types today. And for those of you who have been coming to this symposium for many years, there are a lot of different floor types for mass timber. We have MPP floors, we have CLT floors, we have CLT concrete composite floors. We have mass timber floors with mass timber beams. We have mass timber floors with steel beams. So when should you be using one over the other? What are the trade-offs in using one or the other? What is more beneficial to certain occupancy layouts versus others? And that's really where we're collaborating with Mark to build out that a tool that would be able to be utilized for that also incorporates LCA. Okay, so some results. In our vibration test, I'm going to run through this really quickly as like a preview, then you can talk to me later. So this is vibration results, and what I want to highlight here is that we really saw no influence in the natural frequency of the beam as you varied the connectors. We also then calculated what the natural frequency would be for only the CLT, and so one is that the connectors are not being engaged at these low amplitude loads, and we are not actually activating the full beam or the full girder here. The natural frequency of these beams is very close to just the natural frequency of the CLT. And so we have this huge stiffness differential between our steel beams and our CLT, and that's going to keep being a theme along these tests. So we then took a bunch of these different connectors I'm showing on the bottom of the screen, bolts, screws that were counterbored down through the CLT inserted from above, and then screws inserted below the bottom flange. And we performed some flexural stiffness tests. We cycled through some service level loads, keeping everything within the elastic region. We measured the slip at the connectors, and then we were able to calculate the flexural stiffness. And these numbers don't really mean much in absolute values, but what I wanted to show is that we have this increased flexural stiffness as we go from our bolted connectors to our screws inserted from below. And that can be explained by our small scale direct shear tests. On the left is our bolted connectors. Our yield slip, the slip at which the bolted connectors yield, become engaged with the CLT, is this gray line over here. But our experimental slip is all the way down here, right? So we have basically no slip at the end of these and at the end of these beams. So this is resulting in no composite action. When we looked at screws from above, we can see that the yield slip and the experimentally measured slip during the flexural stiffness test was about the same. So we were getting a little bit more composite action. And when we looked at screws from below, we see that our experimental slip that we're measuring during the tests is above our yield slip. And so we're getting a bit more composite action. Still not a lot of composite action, but a little bit more. All right, if we look at, to kind of give us reference, right, a lot of us are just really used to steel concrete composite action. The numbers don't really mean anything, but what I want to show is that this is where our shear studs yield. All right, our shear studs are engaged with that concrete. And so we see yielding at very, very low levels of slip. And so we're able to have composite action under service level loads. Whereas when we have our steel timber, right, we're not getting that composite action under service level loads when we have these screws that are spaced kind of far apart along the length of the beam, because our screws are very ductile. They're amazing. They bend and bend and bend, but their yield point is after a lot of deformation. And so we kind of don't want that in our connectors if we want composite action at these service level demands. Okay, so then we took some of these beams and we loaded them to failure, and I'm only going to feature one of these. And so this is what happened. The beam failed after we deflected past its out-of-plane support. So we had some out-of-plane bracing right here. And so once the deflection exceeded where that was applicable, the beam failed in lateral torsional buckling, and you can see that the CLT panels kind of went along with it. And so if we take what I'm showing here is the slip of the connectors versus the moment on the beam. This is where our connector slip is when we hit the yield capacity and the plastic moment capacity of the beam without the CLT deck, right? So we're actually yielding that steel beam prior to yielding the shear connectors, which is not actually how we design steel concrete composite beams. It's kind of the opposite way. And so our connector yield is all the way up here. And so this project has really allowed us to explore these beams, the way that they function, and kind of the mechanistic behavior of what is happening, so that we can design our connectors for this system, for this stiffness differential, and then also begin to evaluate the trade-offs in our floor construction. We are doing large-scale diaphragm tests next summer on this system, so stay tuned next year for some fun results from that. And I'll be in Emerson with some of the beams, and you can come ask me questions there.